This is Rosen, Discrete Mathematics and its Applications, section 13.3. These are finite state machines with no output. The section summary, although for this video we will only discuss sets of strings. And before we do that, I'll give a little bit more mention of what a finite state machine, about the finite state machine with no output. First of all, the finite state machine with no output has another name we'll see later. It's a finite state automaton, or FSA. So a finite state machine generally implies output, and a finite state automaton implies no output. But what it does have is it has what are called accepting states or final states that are designed for recognizing languages. So with an FSM, we recognize a language by always having an output of 1 at the end of a word. With an FSA, we will recognize a language by the words in that language ending in a final state or an accepting state. All right, well, kind of given away that we're going to be talking about words and recognizing them. How do we build up those words? Well, we build them up from the vocabulary. So remember, for a language, it's going to have a vocabulary, the set of symbols that you can build words with. And then if the star represents all possible strings using those symbols. All right, so now we want to consider the set of all possible strings under a vocabulary, and then A and B will be subsets of that set of all possible strings. Now, if I want to create a new set called the concatenation of A and B, we'll denote it by setting A to the left and B to the right. That'll be the set of strings x, y, where x comes from A and y comes from B. So it'll be a new set of words from our vocabulary. Will be a subset of V star, but they will be different than A and B. Here's an example. If I've got my vocabulary is 0 and 1, that means V star is a set of all possible bit strings. A is a subset of the set of all possible bit strings and contains 0 and 1, 1. B, another subset of all possible bit strings, contains 1, 1, 0, and 1, 1, 0. Now, if I want to do the concatenation of A and B, I will take every possible combination of a left portion from A and a right portion from B. So for instance, I can create 0, 1 by taking the 0 from A and the 1 from B. I can take 0, 1, 0 by taking the 0 from A and the 1, 0 from B, etc. And I can create another set of words by taking B concatenated with A. And in this case, I can create 1, 0 by taking a 1 from B and a 0 from A to create 1, 0. And so you can see the set is different. B concatenated with A gives us a different set of words than A concatenated with B. And since we can concatenate sets of words, one with two different sets of words, one with another, we could also just as easily concatenate a set of words with itself. So that gives rise to the concepts of powers of A, where A is equal to A to the first power. A to the 0 power is just the set containing the empty string. It's not the empty set, but it's the set containing the empty string. A squared is the set A concatenated with itself. So all possible combinations of concatenations of elements from A with another element from A, or the same element from A. And then A cubed would be A concatenated with A squared. A to the fourth would be A cubed concatenated with A, and so forth. All right, now we've already said that A is a subset of V star, so when that's true, we can identify something called a Kleene closure. That's the pronunciation, Kleene. It's denoted A star. And the way we create that is by taking the union of all powers of A and creating a set containing all of those. And A star contains arbitrary long strings of elements of A because we consider an arbitrary number of them. We also include A to the 0, which means that the empty string will always be the element of a Kleene closure. Let's look at a couple of examples. If I have A equals 0, what is A star? Well, it's just going to be the set of words that have only zeros of arbitrary length, and including no lengths. Remember, lambda is also an element of that. So when n is 0, 0 to the 0 means no symbols at all or the empty string. Of course, 1 would mean there's 1, 0, 2 would mean there's 2 zeros, etc. Since B is the same as my vocabulary, then B star will equal V star. That is the set of all possible bit strings. And C is the set containing 1, 1. So if I'm going to concatenate that with itself any number of times, I'm going to get a set of words that is arbitrarily long but has an even number of ones only, including 0 ones, which would be the empty string. All right, so that is a discussion of how we build up strings using concatenations and the definition of the Kleene closure for sets.